So here we're going to talk about the ideal gas equation, sometimes also called the ideal gas law. We'll talk about deriving the ideal gas equation from these other gas laws that the simpler gas laws, and talk about some of these applications for the ideal gas equation. Okay, so we had talked about Boyle's law, Charles' law, Avogadro's law, and how we could combine essentially all of those together into that combined gas law. This is very similar to that combined gas law, but we're adding in one feature here, and that is a gas constant, which is capital R. So this is the famous equation PV equals nRT. PV equals nRT is definitely something you're going to need to know. So there are four aspects to gases. We have a pressure, a volume, number of moles of gas, and a temperature. And then R is just a way to help us interconvert between all of those. So R, the most common R that we're going to be dealing with, you can see there's lots of units for R, essentially. The one that we use most commonly is 0.08206 liters times atmospheres per mole times Kelvin. So this is giving us an indication of what units we need to have in our ideal gas equation. So pressure needs to be in atmospheres if we are using this numerical value. Our volume needs to be in liters, our temperature in kelvins, and N needs to be in moles of gas. So these units will end up canceling and making this in equivalency. So what's really nice about PV equals nRT is if you know three of the four variables associated with a gas, you can always solve for the fourth. So let's say you know pressure, volume, and number of moles. Well, you could find out what temperature that's at, right? So one equation, one unknown is solvable. So if you ever know three of the four, you're going to be able to figure out the fourth since we know the gas constant here. Again, there are a few other strange ones in here that we will very briefly talk about in the future, but don't worry too much about that. We're pretty much always going to be using liters times atmospheres per mole times Kelvin. And it is important that you know what the units are for that, because it will help us indicate what these other variables, the units for these other variables. Okay. Something that is going off of the ideal gas equation is something called the molar volume of a gas at STP. STP is called standard temperature and pressure, which is a little unfortunate because standard temperature and pressure, it's not that standard. So pressure at 1 atmosphere is very standard, but standard temperature is 0 degrees Celsius, which sometimes it is tempting to believe that should be room temperature, like 20 degrees Celsius or 25 degrees Celsius, which are common room temperature temperatures. But just remember STP, it's 0 degrees Celsius in 1 atmosphere. And really 0 degrees Celsius, less important. Remember 0 degrees Celsius is 273.15 Kelvin. So that's really, really what we should be using in that situation. Let's say we were to solve our ideal gas equation for volume. So remember PV equals nRT, divide both sides by pressure, and you would get volume equals nRT divided by P. Let's say we have 1 mole of gas. So here we have 1 mole of gas. Our gas constant, liters atmospheres per mole Kelvin, times our temperature in Kelvin divided by 1 atmosphere. We would get the volume of 1 mole of gas at STP to be 22.41 liters. And this is convenient because we frequently will talk about ideal gases at standard temperature and pressure at STP. So just by using PV equals nRT here, we know 1 mole of gas. We always know R, so we're never really going to talk about that. We know the temperature and we know the pressure. We can solve for the volume. So this actually turns into a pretty simple conversion. 22.4 liters of gas equals 1 mole of gas. Again, you can only use this conversion factor in our dimensional analysis if we are at STP. This is something that certainly many of us will memorize, But if we're not at STP, it's no big deal. If we have a different temperature and a different pressure, it's totally fine. We can just plug those into this equation, PV equals nRT, and find a volume. So this is a shortcut that isn't particularly useful in my mind, but it is something we do deal with STP fairly frequently. So this is a quick way to interconvert between amount of gas, meaning moles of gas, and volume of gas, the number of liters of gas. So yeah, these are conversions set up in a way that you're familiar with as a way of converting between volume and number of moles. So let's try one of those. Calculate the volume of a mole of ideal gas at room temperature, 25 degrees Celsius and 1 atmosphere. So if you tried this where we just use that ratio, 1 mole of gas equals 22.4 liters, that is not appropriate because we are not at STP. STP was 1 atmosphere and 0 degrees Celsius. Unfortunately, we're at 1 atmosphere and room temperature, 25 degrees Celsius. It's not a big deal because we can just plug that in. PV equals nRT. Pressure is 1 atmosphere, 1 mole of gas. Our temperature, remember, we need to be in Kelvin, so 298.15 Kelvin is 25 degrees Celsius. We always know R. And we just plug and chug there. So we get about 24.5 liters. It's close, but not exactly 22.4 liters. And it makes sense that the volume is a little bit larger, right? We have a little bit of an increased temperature. Increased temperature would increase the volume. So we see a little bit larger volume than that 22.4 liters. All right. There's some other applications to the ideal gas equation. So for example, we can calculate the density of a gas and also the molar mass of a gas. But density of a gas, so here this capital M is molar mass of the gas, so grams per mole. And so that's mass divided by N, the number of moles. Density is also mass divided by volume. So just quickly in looking at this, you can have the molar mass of the gas divided by density, and that would actually be N over V. These are both in the ideal gas law. So we can replace those in the ideal gas law. So let's set it up where N over V equals RT over P. So this is PV equals nRT, but we've rearranged it. So we can actually get molar mass in there and density. And once you get molar mass and density in there, you can solve. So like let's say I solve for density, I would get this: density equals PM over RT. Again, M meaning the molar mass of the gas. Or then I could also solve for M in this, and so I could get the molar mass. If I know, so molar mass equals the density times RT over P. A lot of times, I wouldn't necessarily memorize these two equations because you can get to them just by knowing the definition of and the units associated with density and with molar mass, and use the ideal gas law and replace those. And also, if you were to look at the units, you could do dimensional analysis and look at the units to make sure the units do come out to grams per mole, let's say, or do come out to grams per liter, for example. So just make sure that that's appropriate here instead of just the plug and chug situation. So this is what one of those could look like. Carbon dioxide is effective in fire extinguishers, partly because its density is greater than that of air. So CO2 can smother the flame that by depriving them of oxygen. Air has a density of approximately 1.2 grams per liter at room temperature and 1 atmosphere. Calculate the density of CO2 at room temperature. So 25 degrees Celsius and 1 atmosphere. All right, so the density of air is 1.2 grams per liter. Temperature is 25 degrees Celsius. So 25 degrees Celsius is 298.15 Kelvin. Pressure is 1 atmosphere. And we also are going to need the molar mass of CO2, and that's 44.01 grams per mole. So this is our setup. We could use that equation from the prior slide. Density equals pressure times molar mass divided by RT. and you plug that in, and you should get about 1.8 grams per liter. So here we're seeing that we have a density just a little bit more dense than air. So that's how we would go about doing that. Again, we could, there would be other ways to do this, where you just kind of start with solving, going through intermediate steps instead of starting with this equation. But all right, here's another one. A company just patented the new synthetic alcohol for alcoholic beverages. The new product is said to have all the properties associated with ethanol, but none of the undesirable effects, such as hangover, impairment of motor skills, and risk of addiction. The chemical formula, however, is proprietary. You analyze a sample of the new product by placing a small volume of it in a round bottom flask with a volume of 511 milliliters and an evacuated mass of 131.918 grams. You submerge the flask in a water bath at 100 degrees Celsius and allow the volatile liquid to vaporize. You then cap the flask, remove it from the water bath, you weigh it, and determine the mass of the vapor in the flask to be 0.768 grams. What is the molar mass of the volatile liquid, and what does it mean with regards to the new product? Assume the pressure in the laboratory is 1 atmosphere. All right, so there's a lot going on there, right? One of them is we can get to the density of the volatile organic there, right? We have the mass of that vapor, which was 0.768 grams. And we have the volume of the flask, which is 511 milliliters, right? So grams per milliliter, or grams per liter, right? We could convert milliliters to liter. So we could get the density. And then from the density, really, if we don't know what this chemical is, getting the molar mass is really useful, right? So really, we're trying to find the molar mass of that volatile organic liquid. So remember, if we had the density, we could then get the molar mass. So this is what this would look like. Again, we're having the density. We have mass over volume. I converted this to liters, so we get 1.5029 grams per liter is the density for this liquid. The temperature is converted to Kelvin, 373.15 Kelvin. Our pressure is 1 atmosphere. And so the molar mass, which is the scripted M in grams per mole, is the density times R times T over P. You just plug all that in, making sure that our density is in grams per liter, because liters need to cancel and I need grams on top for my molar mass. And I find 46.02 grams per mole is the molar mass of that unknown liquid.